All right, so we're going to go ahead and start chapter 5, which is all about probability. So before this lesson started, you guys should have done your activity where you guys wrote down 10 fake outcomes to a coin toss and then actually tossed a coin and wrote down those real outcomes. And so when I usually do this when I'm there, basically when I go around to each group to check and see which 10 outcomes are real or fake, what I look for are things that look fake. So here's what I'm saying. So I have two outcomes here of 10 coin tosses. And what I'm noticing is the one on the right starts with 5 tails. And that seems pretty silly. Like that probably wouldn't happen in real life. But actually, if you're faking 10 coin tosses, you know that probably wouldn't happen in real life. And so there's no way you would ever actually write tails, 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 or something like that. So actually, my guess would be, in this case, that this would be the real list of coin tosses, and then I would assume this was the fake coin toss. And the reason why I would say that is because we all know that the probability of landing on heads or tails is 50%. For a fair coin. And so if I'm faking 10 outcomes, I'm going to make sure that 50% of my outcomes are heads, 50% are tails, and then I'm going to try to mix them up a little bit. And actually, if you look at the fake one, or the one that I'm assuming is fake, I have exactly 5 heads, exactly 5 tails, and I've spaced them out a little bit. Whereas the real one, look, you're tossing a coin 10 times. Anything could happen. If the first outcome I have is tails, if I land on tails the first time I flip a coin, well, that has nothing to do with what's going to happen the next time I flip the coin. I could, of course, land on tails again. In fact, I have a 50% chance of doing so. So if you're wondering if there was a trick to this, there was. Basically, I was looking for strings of tails or heads. And so or anything pattern wise. So like for another one that you might see is heads, tails, heads, tails, heads, tails. Okay, well that's a little on the nose, but again, that could totally happen in real life. Whereas if you were faking it, you would sort of see that and think, okay, well that's a little ridiculous. So basically what we're getting at here is this. There's a lot of stuff you guys know about probability, but we're going to sort of analyze little parts of it. So one of the things that we're going to analyze is, listen, if I'm tossing 10 coins, in the short run, just 10 coin flips, anything can really happen. I could end up with 50% heads and 50% tails. But if you kind of pause this for a second and ask each group, I'm betting that there were groups that got only 3 tails or 3 heads out of 10. That's not crazy for 10 coin flips. That's not unheard of. Whereas if you were to flip a coin 100 times and you only got 30 heads or 30 tails, that's a little weird. So one of the things we're going to look at is probability in the short run versus the long run. And in fact, that's how in AP Stats we're going to define probability. So we're going to define probability as a long-run relative frequency. And you guys may or may not remember this, but relative frequency is a fancy term for percent. So it's a long-run percentage. So meaning, if I flip a coin 6,000 times, about half of the coin flips I get should be heads and about half of them should be tails. So in the long run, 600 coin flips, 50% of my coin flips should be heads, 50% should be tails. And that is how I'm going to define probability. So let's write some stuff down. So we're going to define probability as a number between 0 and 1. Oh, we're doing this again. That describes the proportion of times an outcome would occur in a very large number of trials. Let me see. Okay. I should say trials. There we go. All right. So basically the way we're going to look at this at first is sort of using the coin flip idea of what we just described. And so we're going to talk about something called the law of large numbers, which is kind of goes hand in hand with our definition of probability. So our law of large numbers basically says as we observe more and more outcomes of some kind of chance process, like flipping a coin or rolling a die, then the proportion of times something happens should approach a specific value. So meaning, in English, if I flip a coin an infinite amount of times, the percentage of times that coin lands on heads should get closer and closer and closer to exactly 50%. Now, maybe in the first 100 flips, you might be looking at like 48%. But when we get up to like 1,000 flips, we might be closer to like 49.6%. And then if I look at 10,000 flips, I would be closer to 50% on the dot. And so that's essentially what the law of large numbers is saying. is saying. So let's write that down as well. Oops. So if we observe more and more repetitions of a chance process, the proportion of times a specific outcome occurs approaches a single value. So if you are a calculus person, you're sort of thinking of the law of large numbers as almost a limit. It's the limit as the number of repetitions approaches infinity of the probability of something happening. Kind of think of it that way. So one of the ways we show what we mean by this is by sort of a graph. And so I'm going to draw this graph for you. So I'm going to pause this, draw the graph, and then you will instantly see it. You can go ahead and copy it down, but basically the goal is not that you would actually have to make this graph in AP Stats, but that you would be able to look at it and understand what it's saying. So give me a second here. Okay, so this is a graph showing the number of coin flips that somebody does versus the proportion of heads. So meaning if I flip a coin 2 times and I get heads 1 time, then my proportion of heads would be 1 out of 2 or 50%. So this is sort of what the law of large numbers is saying, and this graph, by the way, is often given, so they want you to be able to read it and understand what it's saying. So to start off with, after 1 coin flip, let's say my first coin flip is a head. That means 100% of my coin flips so far are heads. So after 1 coin flip, I land on heads. 100% of my outcomes are heads. Okay. Well, after 2 coin flips, it looks like the second one I got tails. So now I only have my 1 head from the first trial out of 2 total outcomes. So 50% of my outcomes are heads. And then as you see, as I keep flipping coins, my percentage of heads is going to fluctuate a little bit. And it fluctuates kind of a lot at first, but the more and more and more flips that I have, the closer and closer that proportion is going to get to 50%. And that's basically what the law of large numbers is saying. Whoa, sorry, time out. I just zoomed out way too much. This is crazy. Give me a second here. Sorry, children. I don't know what happened. I do not know, but I'm going to fix it. There we go. Okay. We're back, people. We're back. Can I fix it this way? Ooh, too much. There we go. Okay. So this proportion, okay, is getting closer to 50%. And since that proportion is getting closer to 50%, that proportion is the probability of getting heads. And so that's sort of a couple of things. This is sort of a picture of the law of large numbers. And the law of large numbers, if you want to think of it this way, is sort of how we define probability. It's, hey, in the long run, what percentage of the time do you land on heads? Okay. So you're going to see a few questions that are on your homework and homework quizzes that are going to ask you about law of large numbers, all of that. And so we're going to look at an example where you would have to talk about probability using this kind of lingo. So it says, example 1, the probability that a lie detector incorrectly predicts that a person is lying, when in fact the person is telling the truth, is 0.08. Interpret this probability as a long-run relative frequency. So here's sort of where we're going with that. They want you to say what this 0.08 thing means in the language of long-run relative frequency. Oopsie. So if you feel like you got that and you want to give it a shot, go ahead. Otherwise, keep watching and we'll talk about how to do this. Okay. So in the language of long-run percentages, basically what this is saying is, all right, as we keep using this lie detector, it seems like this lie detector is going to incorrectly predict that a person is lying about 8% of the time. So I said as the lie detector keeps getting used, it incorrectly predicts that a person is lying about 8% of the time. If they asked you this question about coin flips, they said, hey, the probability of flipping a coin and getting heads is 50%. Interpret this as a long-run relative frequency. You would say if we were to flip a coin many, many times, the coin would land on heads about 50% of the time. So when they ask you to interpret probability as long-run relative frequency, this is what that looks like. Okay. All right, we got a couple other examples, so go to the next page. Now this one you should have been able to do in like, what, 5th, 6th grade? So I'll read the question and then I want you to pause this, do it, and then we'll check answers, make sure we're good. So it says probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow with each statement. So read statements A, B, C, and D. Obviously you have probability choices up here and there are more of them than there are questions. And so choose the most appropriate probability value for each one. Pause this first for a few minutes or even a minute, and then we'll check. Okay. So check your answers. The first one, this outcome is impossible. It can never occur. That should have been 0. The probability of that happening is nothing. It's not going to happen. B, this outcome is certain. That should be 1. So there's a 100% chance that will happen. C, this outcome is very unlikely, but it will occur once in a while in a long sequence of trials. So for that, I would have chosen 0.01. The best wrong answer would have been 0.03, but that's 30%. A 30% chance of happening is not, I wouldn't call that very unlikely. I don't even know. That's not particularly unlikely. I would call 30% chance sort of unlikely at best. So you should have gotten 0.01. And then finally, D, this outcome will occur more often than not. I would put 0.6, 60%. So it will occur more than 50% of the time. It will occur more often than not. I would have chosen 60% versus 99% because 99% is almost 100%. That's you're most likely to happen. It's not a guarantee, but it's pretty close, something like that. So those are the answers you should have had for probability. Hopefully this was pretty easy. So let's move on to example 3. Okay. So we're going to have to reminisce back to the probability skills that I'm sure you're super strong with. Let's do this. So it says, a few years ago, an advice columnist published a letter from a distraught mother of 8 girls. She and her husband had planned to limit their family to 4 children, but they wanted to have at least 1 boy. When the first 4 children were girls, they tried again and again and again. After 7 straight girls, even her doctor had assured her that the law of averages was in her favor. And so what I would like you to do is find the probability that a couple would end up having 8 girls in a row. Now, again, we haven't talked about how to do this. This is sort of hearkening back to, 6th grade probability. And then again, in geometry, you were supposed to have done this. I know you might not have done so, but I want you to pause this, talk to your group. What is the probability that a couple would end up having 8 girls in a row? Okay. So, assuming that the probability of having a girl is 50%, then the probability of having 8 girls in a row would kind of look something like this. So I put G to represent girl. You would literally have 8 girls in a row. And the probability of each of those girls is 0.5. And so to find the probability that a couple would have 8 girls, you would be multiplying 0.5 times 0.5 times 0.5 8 times. So it would be 0.5 to the 8th power, which would end up being 0.0039. So that's less than 1%. That's very unlikely, I would say. So what is the probability they have 8 girls in a row? It's very unlikely. However, sort of a weird idea. Part B, given that the couple already has 7 girls, so they've already got 7 girls, they're going to have another kid, what is the probability the next kid will be a boy? Well, it's 50%. Each kid is a different kid. It's an independent kid. And so the probability that the next kid is a boy is 50%, since each kid is independent of the next. So this is sort of a weird dichotomy. Like if you think about it, like really think about it deep down, it can be a little philosophical here, people. I'm not kidding. The probability of having 8 girls is really, really low. But assuming you've already had 7 girls, the probability that you have an 8th girl, the probability that the next kid is a girl or the next kid is a boy is still 50%. Doesn't matter what happened before. So this is the deal. This whole example is to talk about this law of averages. This is sort of a pop culture stats idea. This is not a real stats idea. And it basically says, it assumes that the short run will look like the long run. So meaning, if I toss a coin 6 times, the law of averages, quote unquote, says that 3 of those times I should get heads. But in reality, 6 times is not the long run, it's the short run. And pretty much everything could happen. Or anything could happen. Go back up to your graph here. If you notice, in the short run, up to 6 trials, you got crazy stuff going on. It's only later, after you've looked at a bunch of trials, that your probability starts evening out to 50%. And so the law of averages is not a real thing, but what it tries to do is it assumes the short run's gonna look like the long run. So if I flip a coin 2 times, I should get exactly 1 head. If I flip a coin 10 times, I should get exactly 5 heads. If I have 4 kids, 2 of them should be girls, 2 of them should be boys. So that's what the law of averages says, but it's not real. It's not mathematically sound. So let's write some stuff down. So the law, oh my, Microsoft Word killing me again. So the law of averages assumes the short run will look like the long run. And then, for example, if we flip a coin 6 times, 3 should be heads. And basically the takeaway for this is not mathematically legit. And so contrast this with the law of large numbers. So the law of averages says, I've been flipping coins, so I'm flipping a coin 6 times. The first 2 that I get are tails. I should be seeing a head pretty soon. That's what the law of averages said. The law of averages is a perfect picture of this example. I've had 7 girls. I must have a boy. Like, the next kid has to be a boy. That's what the law of averages said. No. Contrast that with the law of large numbers. The law of large numbers says if I have 700 kids, half of them should be girls, half of them should be boys. But 7 and 8, that's still short run. Anything could happen. So when you see law of averages, a lot of times in homework questions or sometimes in AP stuff, they'll say, hey, what's wrong with this statement? And basically, usually what's wrong with the logic is you're trying to treat the short run like the long run. And so, by the way, this story evidently is a real story, and they did try for another kid, and they did have a girl. So, whoopsies. Sad day for them. Anyway. Girls are fun clothes, just saying. So, let's look at one more. Yeah, one more. So it says, according to the Book of Odds website, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Okay, so part A, explain what probability 0.61 means in this setting. And I know that's kind of an awkward question, and most of the answers I get are usually, it means the probability is 61%. Give me more, talk to me about the long run frequency, that kind of thing. And then B, why doesn't this probability say that, that in 100 U.S. adults, if 100 U.S. adults are selected at random, it's supposed to be if, my bad, 61 of them eat breakfast regularly. So why doesn't the probability explicitly say, if we take 100 U.S. adults, 61 of them exactly eat breakfast regularly? So pause this, write an answer, and then we'll come back and discuss. All right, so explain what the probability 0.61 means in this setting. So hopefully you went something like this. So if we took many U.S. adults, about 61% of them eat breakfast regularly. So that's what they wanted you to kind of go with. Hopefully you didn't use the word probability to define probability. That's kind of the goal. And then part B, why doesn't this probability say that if 100 U.S. adults are selected at random, 61 of them eat breakfast regularly? So something like this, but probability is not a short-run guarantee. And so this means that if 100 adults are selected, we think around 61 of them will eat breakfast regularly, but not necessarily exactly 61 of them. Now, maybe 61 of them will. Maybe they won't. We expect it to be around 61. So hopefully you said something like that. And then we have one more kind of thing to start off today. So our last piece, whoopsie, my bad. So our last thing we're going to define, and then you have an activity to kind of end this lesson, is going to start into what you guys are doing in the next lesson, and that is simulation. So we did a couple of examples today looking at coin flips and having boys and girls. And we looked at those examples because we know the probability of each of those is about 50%. Sometimes we don't really know probabilities, and so one of the best ways to estimate them is through something called simulation. And that is maybe what it sounds like, maybe what you've heard before in other classes. But a simulation is an imitation of an actual process. So in this case, simulation is the imitation of a chance process. Sorry, that's a C. that accurately reflects the process exactly. And so we're going to get into more detail of what that looks like later. And then sort of as a closure today, you guys have an activity, where you are actually going to do a little simulation. And you should still have the coins from the coin flip that you just did. So you can go ahead and do that and write down your responses below. You are all going to get, well, you might all get potentially different answers. And that is your lesson today. So have a lovely day.